Hi, in this video, we'll be discussing the quotient rule. Got 3 examples. I'll tell you what the quotient rule is, and then we'll just apply the quotient rule. And then we might do the derivation of the rule algebraically in a different video. So we've got a derivative of a quotient. We're going to call this this top function the high function, and this bottom function the low function. Sometimes I will abbreviate the top one as HI and the bottom one as low, LO. And here's a mnemonic device. The derivative of high over low is low d high minus high d low over low low. And the d is a derivative operator. It applies to whatever's in front of it. So I'm thinking through this rule. I'm thinking through this mnemonic every time I write down my quotient rule. There's low, so that's the bottom function. D high, so that's the derivative of the top function, minus high, which is the top function, times d low, the derivative of the bottom function, over low low. That's g of x quantity squared. So that's our quotient rule, and we'll apply it in 3 examples in this video. We've got the derivative with respect to x of secant of x over x cubed plus 2x. Now, according to my quotient rule, I get low d high. So I write down my low function or my bottom function first. Since it's got multiple terms, make sure we add parentheses there. It's low d high, the derivative of the top function is our d high. Derivative of secant of x is secant of x times tangent of x. And then we subtract the high function, which is just secant of x. And then we multiply by d low. And the derivative of this bottom function is just the sum of, or derivative of a sum. So derivative of a sum is the sum of the derivatives. Derivative of x cubed, it can be found using the power rule. So you bring the power down, multiply by x, so the 1 less power. And then you add the derivative of 2x. Derivative of a constant times x is just a constant. So that's low d high minus high d low, all divided by low low. And that's our derivative. Typically, I like to put the polynomial terms or polynomial factors in front of the trig function factors, just to make it clear that this trig function is multiplying that entire polynomial. Otherwise, sometimes it can be ambiguous. If this one isn't in parentheses, it can look like this polynomial is multiplying the x, and then we take the secant. What we mean is take the secant of x and multiply by the polynomial. So I'll put the polynomial out front. Polynomial times the secant of x, and it gives you the same thing. And remember, this is a formula for the slope of this function at any x value in the domain. A couple of things that we want to think about here before I start graphing this function is what the domain of this is. That denominator factors. This is the derivative with respect to x of secant, which is 1 over cosine of x, divided by this. If you look at these two terms, you see they have an x in common. So that's x times x squared gives us the first term. X times 2 gives us the second. And you see that this denominator will be 0 whenever x is equal to 0. So the domain of our function is all real numbers x, except for x equals 0. And any x values that cause the cosine to be 0. Now this wasn't written here, but it was implied by that secant. Secant is defined in terms of this quotient. Cosine is 0 at all of the odd multiples of pi over 2. So x cannot be pi over 2 times an odd number. And we can represent all of those odd numbers by the expression 2n plus 1, where n is an integer. Because if n is an integer, if you double it, you're going to get an even number. And then if you take an even number and add 1, you're going to get an odd number. So we're saying x can't be an odd multiple of pi over 2, and x can't be 0, but any other real value will work. So let's graph this function and this function and the tangent line and see that the slope of the tangent line is actually given by this formula. I know that this is very complicated looking, but again, it's just a formula for the slope. We just want to emphasize that. So this is our function. I added some of the vertical asymptotes. We know that when x equals 0, the function is undefined. When x equals negative pi over 2, that's where our secant is undefined. Positive pi over 2 as well. So any of those multiples of, or those odd multiples of pi over 2, we're going to have some problems. I'll just graph the other two. X equals negative 3 pi over 2, we're going to have an issue. X equals positive 3 pi over 2, we're going to have an issue. Oops. Positive 3 pi over 2? That one worries me a little bit. Yeah, I'm not really sure what happened to the graph there. Nope. Actually, we do have an asymptote. It was a little bit difficult to see. But it's there. It's actually there. It's a little bit harder to see from far away. But this is our function. And let's say we're going to be between 0 and let's say positive pi over 2, or maybe on this branch from negative pi over 2 to 0. We've got a point of interest there. Just added those asymptotes so that we can have a better sense of what's going on. And this is actually my derivative. This is what we computed by hand on our paper. Now Desmos actually gave me an error message. I wanted to show you that. See, it says, use parentheses around the argument of secant. I don't really think that's necessary, but for some reason Desmos wants it that way. So we're going to add parentheses here. It's going to add parentheses around the arguments of secant and tangent. Gosh, it looks like an entirely different graph, doesn't it? All right. So that green graph is the graph of the derivative. And we want to draw this tangent line, which is just f evaluated at x naught plus the derivative at x naught, which is your slope, times x minus x naught. So it's a change in y over change in x times a change in x, which gives you a change in y, plus the original y gives you the new y. And at x naught equals negative 0.8, we're right there. And this derivative gives you the slope. The claim is that the slope is approximately negative 0.562. I wonder if that's true. Let's zoom in a little bit. Say, okay, well, what is that derivative? Well, we can just use rise over run to calculate. So it looks like we go from about negative 0.7 to approximately negative 1.1. So negative 0.7 or negative 1.1 minus that negative 0.7 is going to give us a negative 0.4. And then we're running to the right. And it looks like all of these boxes are 1/10 apart. So as we go from here, from this vertical line to the vertical line that intersects with our point of interest, we're going to go from negative 0.8 all the way back to 0. So that's 0.8. And so we've got a slope of approximately, what was that? Negative 0.4 divided by 0.8. So about negative 1/2, which is consistent with what we get on the derivative graph. And if we change our x naught, we can get different slopes, and the slopes are given by the values of that derivative. In this case, at this point, that slope, according to the graph of the derivative, is about -3, and that's consistent with what we see on the picture. It looks like we go down 3 and over 1. Looks approximately true. that we get down 3 and over 1. Now, some of these vertical lines, graphs of the tangent lines are a little bit distracting now, so maybe we should get rid of those to make the graph a little bit cleaner. But now we see both our graph, the derivative graph, and the tangent line. And the value of the derivative is the slope of that line. And you might be saying, okay, well, show me that that's true with an x value where the slope is positive, or the slope is going to be positive over here. Let's just move this point of interest to the other side and check out what the slope is at x equals negative, or x equals negative for 1.45. What's the slope? Actually pretty steep. Looks like the slope is 9.544. It's a very, very large slope. Go back to that point. Does that look like we go up 9.5 and over 1? Yeah, I think so. That seems reasonable looking at the graph. So that is an example of how we use that quotient rule to find the derivative, and how, again, the derivative is just a formula for the slope of the tangent line. In the next two examples, we're just going to calculate the derivatives, and then maybe we'll look at the graphs really quickly, and then we'll be done. So the derivative of cosine of x divided by natural log of x is the derivative of a quotient. So we can find that using the quotient rule. We call this the high function, and this is the low function. Using our mnemonic, we have, again, low d high minus high d low over low low, the derivative of our product, or derivative of our quotient. So we'll have low, that's the bottom function, times the derivative of high, or the derivative of the top function. The derivative of cosine is negative sine of x, minus high, that's the cosine function. D low, the derivative of natural log of x is 1 over x. And that was one of the rules we just stated. And then low low is that bottom function squared. And so then we can simplify this term and this term have a negative in common. If you want, you can multiply by x over x to clear the complex fraction. And so we end up with this. X times that first expression is x sine of x times natural log of x. And then x times the second expression is 1 over x times x, which is 1. And then we've got a cosine there. Put some parentheses around all of that, factor the -1 out front, get the natural log of x quantity squared in the denominator. And that is the slope of that function. So we'll graph those in a bit. Let's do one more example by hand, and then we'll look at the graphs again. And this one I've got sine of x divided by log base 2 of x. And so we'll have low d high. The derivative of the high function, or the top function, is cosine of x, minus high d low. Our base is a. So in this case, a is 2. So we get natural log of 2, or excuse me, 1 over natural log of 2 times x. That's the derivative of a log base a of x is 1 over log of a times x. And we divide all of that by that bottom function squared. This is low d high minus high d low over low low. And then we want to simplify this as much as possible. To do that, we are going to try to get rid of this complex fraction. So we're going to multiply the numerator and denominator by natural log of 2 times x. That's just multiplying by a well-chosen 1. Multiply there and there. And we end up with x times, oops, natural log of 2 times log base 2 of x times cosine of x. And then here, when we multiply this fraction times this, it's just a 1, so we're gonna have a minus sine of x, all divided by x times natural log of 2 times log base 2 of x, quantity squared. And that's our answer. And again, this is a formula for the slope. So let's look at these on desmos.com, make sure that we're typing everything in the way that desmos.com wants it typed in. And then we'll look at the slope of the tangent line at a particular point and confirm that these are actually giving us formulas for the slope of the tangent line at particular locations. Okay, so this is our example, f of x equals cosine of x divided by natural log of x. I want you to notice that the function is only well defined when x is positive. So we're only going to have a graph to the right of the y-axis, and it's going to be undefined when the natural log of x is 0, natural log of x is 0 when x is equal to 1. So I've graphed that vertical tangent or vertical asymptote there at x equals 1. Now, after we used the quotient rule on pencil and paper and then factored out a -1 and cleared the fractions within our larger fraction, we got this. But notice Desmos gives me an error message again. It wants parentheses around the argument of the sine function this time. So we're going to add some parentheses here. And let's do the same thing for cosine. So after adding those parentheses around the argument of sine and cosine, this is what the graph looks like. And I have selected an x naught equals 2.1. And then labeled f of x naught and f prime at x naught. Let's sketch the tangent line there. So the tangent line is given by the original y value, so that's f of x naught, plus the change in y over change in x, which is just our derivative. That's our instantaneous rate of change at x equals x naught. And then we multiply by x minus x naught, which is just the change in x. So we've got change in x times change in y over change in x is change in y plus the original y value is the new y value. And that gives us our tangent line. And the claim is that this is tangent to the graph at that location, and that the slope of this tangent line is actually given by the function values on the other graph. I want to use that color. I like that color better. Oh, it doesn't look like it's tangent to the graph at all. Got a line that's crossing my graph. See how it doesn't have the right slope? So that tells me I must have made a mistake in my calculations. All right, so let's see what it says. Use parentheses around the argument of sine. I'm gonna add a bunch of parentheses around all of these guys. It's weird, I'm getting the wrong value. F prime of 2.1 is negative 1.5. That's very strange. I wonder if it's using the f defined on this example. So let's get rid of that example for right now. We've already looked at example 2. And then let's look at example 1 again. It's like I'm doing something, I'm getting the wrong answer. I wonder if the computation that we did by hand was incorrect. So let's try to find our error. All right. So we were looking at this function. The derivative of cosine of x divided by natural log of x is low d high. So you have the bottom functions, natural log of x. The top function is a cosine function. The derivative of a cosine is a negative sine function. And then we're subtracting high. So that's subtracting cosine of x times d low, which is 1 over x, dividing by low, that's natural log of x quantity squared. bottom function squared. And then we multiplied by x over x in order to simplify. And I think that's where the mistake is. When I distribute the x here, I get this. When I distribute the x here, I get that. Factor out the negative from both of those. And I forgot that x in the denominator there. Okay, so I think we found our mistake. Now let's go back to the graph of the original function and see if just typing that differently sort of solves our problem. Okay, so I just need an extra x down here. All right, now it looks like it's tangent to the graph. That's interesting. Looks like the tangent line has a slope of negative 0.727. And it looks like it's crossing here at this point. It looks like the function value and its derivative are the same. They're not exactly the same. The function value is negative 0.68 and the derivative value is negative 0.727. But I think because our grid is, because those numbers are so close together, it's a little bit hard to tell that they're different from each other. It might be easier if we choose a different x value. So if we choose this x value here, actually I think I want to make sure that that's orange so it matches the derivative graph. The claim is at x equals 2.6, the y value is approximately negative 0.897. The slope is supposedly about negative 1.79, and we could calculate that. Just go down however many units that is, and then run to the right however many units that is. So it looks like about 1.5 boxes. We're going down in the y direction, and then we go 1, 2, 3, 4, 5, 6, 7, 8 in the x direction. But look at these, look at the grid. You want to look at the grid to make sure. Each of those little boxes represents 1 or 0.2. So this is 1, 1.2, 1.4, 1.6, and so on. So as I go 1, 2, 3, 4, 5, 6, 7, 8 boxes to the right, that is 8 times 0.2 or 1.6. So we're going, we're running to the right 1.6 units in the x direction, and we're falling in the y direction. It's like 1.5 boxes in the y direction. Now let's check out the y-axis. Turns out the grid is the same. This is 0.2 here. So that's negative 0.2, and that's about negative 0.1. So it looks like I'm taking change in y, which is negative 0.3, and then dividing it by 1.6. So let's do that calculation here. Negative 0.3 divided by 1.6. And I get about negative 1.875, which is consistent with the function values on the derivative graph. It's about negative 1.8. according to this. And of course, we're just estimating. So we wouldn't expect it to be exactly the same. But yeah, this formula is actually giving us the right slope. And we can see that when we graph it. And if we made a mistake, and we did make a mistake in this example, we can find our mistake when we notice that our tangent line isn't tangent to the graph. Without the x there, we said that's not tangent, it's crossing the axis. And then we were able to find our mistake and realize that when we put that x there, everything is tangent the way it's supposed to be, and things look good. So that is our example 2. Now let's look at example 3. Example 3 looks like this. Now I used another logarithm. So here we've got log base 2 in the denominator and a sine of x in the numerator. And this is undefined whenever the denominator is 0. Log base a of 1 is 0 because 2 to the 0 power is 1. So that's going to give us a 0 when x equals 1. So we've got that vertical asymptote right there. And we might be interested in the derivative at a particular location. So here's my derivative. It's kind of cool looking, isn't it? And then I want to plot x naught and f of x naught. So just pick an X value. And I think I'm going to change the color of this one to make it match my original function graph. And then I'll change the color of this point to make it match the derivative graph. All right, and let's label those points. So this is the function value at 2.2. Our function is approximately 0.711. And at the same location, supposedly the slope is about negative 0.927. In order to verify that, we can graph the tangent line and then just use the grid to infer or estimate, excuse me, and the slope of the tangent. So we take the original y value, add the derivative, add x naught, and multiply by x minus x naught, same as usual. We do this all the time, so very comfortable with that. And then we'll just use the grid to estimate. So we go down, it looks like approximately 3.8 and divide by 4. So let's see. Negative 3.8 divided by 4. It's approximately negative 0.95, which is approximately the same as the negative 0.927 that the calculator or the Desmos.com website is giving us. So we can see that the slope of the tangent and the actual slope of the tangent line and the derivative values match. And of course you can vary your x values and say, okay, there I should have a 0 slope, horizontal tangent line. And it looks like I do. The tangent slope is 0.013 there. It's really hard to make it exactly 0 on Desmos. Anytime I have hills and valleys, I'm expecting a 0 slope. So at the top here, the slope 0, well, almost negative 0.003. At x equals 7.8. Might look for another 0 slope. That's going to be at that bottom point up. It's past x equals 10, and that's the only range. That's the range of values I gave myself. If I wanted to, I could go from, let's say, 0 to 20. I think I'm choosing the wrong point. The green point is on the derivative graph. I'm trying to vary this one. At that minimum value, where x is 11, the slope is about 0.012. Turns out it's supposed to be exactly 0 on the derivative at the very minimum there. It's pretty close. It's just hard to get it. It's hard to make it exact. Then over here at this location, I would expect a 0 slope. And there, the slope is nearly 0. So again, the derivative graph and the slope of the tangent, or the slope of the tangent line and the value of the derivative are approximately the same. And we can vary that point. They're so close together now. Can vary that point and look at different slopes. To see that they're pretty much the same, pretty much. Now, another thing I'd like to point out before we finish this video is that on the other side of this asymptote, we've got another branch of the graph. So if I get rid of this, my graph comes in 2 branches, one between 0 and 1 and the other from 1 to infinity. I might be interested in this branch between 0 and 1, so maybe I'm interested in my x values between 0 and 1 now. Now it's a little bit harder to see unless I change the range of x values. So let's let x go from negative 0.5 to 1.1. Now the differences are going to be very exaggerated. If I graph my derivative, there it is. Now let's move the tangent line. So it's somewhere in there. And we see that that's a tangent line. It has a negative slope. The claim is that the slope is about negative 5.265. And I think that that could be right. It's a little bit difficult to see because of the spacing on the x-axis. Claim is that we would go down 5 units. So from 0 to negative 5.2 and then run to the right 1 unit. So if I go down negative 5.2 and run to the right 1 unit, do I find another point on the line? And I do, because this is 1 unit in the x direction, and this is actually negative 5 units in the y direction. You just have to make sure that you have those tick marks in sight so that you can see sort of how much each of those boxes is worth in the vertical and horizontal directions. But you can change the point and check that the slope is what it's supposed to be. As we decrease that value of x, we notice that this line is less steep. And so the tangent or the slope of the tangent values are smaller in magnitude, but they're still negative because that line is decreasing. And so, yes, our quotient rule gave us the right formula for the derivative of this original graph. And again, the derivative gives us a formula for the slope of the tangent line at a particular location.